Hello, welcome back. This mini lesson is going to be covering the generation of graded potentials, and I'll talk a little bit about what they can and cannot do. So if we take a look at our navigator picture, we just covered this part right here in the last video. So resting potentials, that was our transmembrane potential, sodium, potassium concentration, electrochemical gradients, and our three different types of channels. We have the chemically gated channel, the voltage gated channel, and the mechanically gated channel. So now this video is going to cover this circle on this picture, on this navigation picture, graded potentials. Before we move on, I wanted to make something very clear, and if you can remember this, it will help you as you're learning the differences between graded and action potentials. Everything along the cell body and dendrites, so all of this membrane that's covering the cell body and dendrites, all over this, these have chemically gated channels. Okay, that's it. Chemically gated channels on the cell body and dendrites. All along the membrane, the axolemma, if you will, starting at the initial segment. We talked about the initial segment by the axon hillock. These have voltage gated channels, and actually all the way down to the synaptic knobs. So all this blue membrane here. So that's really, really important. Cell body and dendrites, chemically gated channels. Axolemma down to the synaptic terminals, voltage gated channels, because those two types of channels they are triggered differently. One is triggered by chemicals, one is triggered by change in voltage. You can only get action potentials where you have voltage gated channels. You can only get graded potentials where you have chemically gated channels. So the location of the channel is directly related to what kind of process can occur at that membrane. If you are on the cell body and dendrites, you only have chemically gated channels, you can only do graded potentials. If you are on the axolemma of the axon all the way down the telodendrite to the synaptic terminals, you have voltage gated channels, you can do action potentials. Okay, that's super duper important. So make sure you are understanding that. If you have a hard time with that, let me know. So we're going to move on to what can happen at the cell body and dendrites because of the chemically gated channels. And these are what we call graded potentials. They're also called local potentials because they only have a local effect. They can't do long distance communication. That's only action potentials can do that. So let's say we have somewhere along the cell body and dendrites, right? Because we have our chemically gated channels. We are at rest, so that's this first picture. Resting membrane with closed chemically gated sodium ion channels. We are at negative 70 millivolts. We do not have any acetylcholine showing up. The neurons just kind of chill. It's just kind of hanging out. Then it says stimulus applied here. So the stimulus is applied right there on the cell body. It's right next to the axon. It's not on the axon. We're still in the cell body. So what that stimulus is the arrival of acetylcholine. So here's the arrival of the acetylcholine, right? The little red molecule binding to its receptor site, opening up the chemically gated channels. We are now permeable to sodium. Following the electrochemical gradient of sodium, sodium wants to rush in and look at what's happening to that transmembrane potential. We're at negative 70 here. At rest, we open the channel. We get a little bit more positive because we're gaining positive charges of that sodium rushing in. So wherever we have those gated channels open, sodium will continue to rush in. Oops, that was supposed to be 65. I'm kind of giving it away here because it will eventually go to negative 60. And this area is negative 65. And the further away that you go from where the stimulus was applied, you're going to eventually fade back into rest because we have no stimulus. We have no graded potential over here. So it is happening. The change in transmembrane potential from negative 70 to negative 60 is happening right where the stimulus is showing up. And then when the stimulus goes away, which is the removal of acetylcholine, those channels will close. The sodium-potassium pump is always working, pumps all that sodium right back out, and we're back to rest. So it's a very local, temporary effect. So in this graph over here, we can see that we start at negative 70 rest. the chemical stimulus is applied, right, because it's chemically gated channels on the cell body and dendrites. Once the chemical is applied, the gates open, we depolarize. So depolarize means going towards zero, going towards more positive. So we depolarize, we're getting close to a less negative number. We're going more positive, however you want to think about it. And at the peak of this graded potential, that's when the acetylcholine is going to be removed. Then we return to rest, which is called repolarization. Okay, so this is a graphical representation of a graded potential. We start off at rest, we might get a little bit less negative, and then we go back to rest. Okay, so these graded potentials, in this particular example, we have a depolarizing event, which means we go from a negative 70 closer to zero. It goes from negative 70 to say negative 60 or negative 65 or whatever. We can also have what's called a hyperpolarizing graded potential. In this case, it would have to be a different gated channel and a different ligand stimulus molecule that's coming in. But in this case, we're at rest. The stimulus is applied, the gates open, but instead of gaining positive charges, what if we gain negative charges? Maybe it's a chlorine channel and chlorine rushes in. Chlorine is a negatively charged ion. If we gain negative charges, we're going to become more negative. That's what hyperpolarizing means. Or what if the stimulus shows up, it's a particular neurotransmitter, and it opens potassium-gated channels? If you remember, potassium flows out of the cell. If we're losing positive charges, that is also a hyperpolarizing event. Okay? Stimulus gets removed, sodium-potassium pump keeps pumping, sodium out, potassium back in, and we get back to rest. Okay? So in both situations, we have a change in transmembrane potential due to the arrival of a chemical stimulus. Once the chemical stimulus is removed, the membrane goes back to resting potential. Now you might be asking yourself, well, what's the point? Like, why even have a graded potential if they're not doing anything? They just change for a little bit and they go back. Well, the issue comes right here at that initial segment of the axon. If the cell body and dendrites with their graded potentials change the transmembrane potential of that initial segment enough, it could trigger an action potential. So these are like the on-off switch or the facilitating, inhibiting messages that if that first set of voltage-gated channels changes enough, then you will be able to get an action potential. Okay, so that's what we're going to talk about next. So this is just a quick little video to cover graded potentials. Chemically gated channels on the cell body and dendrites may or may not produce an action potential on the initial segment of the axon. But we're going to look at that next. So I will see you then. Bye.